Hello, everyone. Good morning, good afternoon, good evening, wherever you are. My name is Siva Segaran. I'm the Senior Director of Business Development at XtalPi in Boston. Welcome back to the Solid State Services webinar. As you all know, we have been organizing several webinars in the recent past with regard to fundamentals of solid formulation that ended last week with a talk from Dr. Eric Diebeck from Pfizer. And several of you have reached out to us over the past few weeks, as well as during the course of the FSF webinar as well, wanting to know more about XtalPi solid state services, capacity, capabilities, resources, so on and so forth. So that's one of the reasons we organize this solid state services webinar, where we have an expert, an in-house expert, who will walk you through our workflow in detail and will answer any questions that you may have about our solid state services. And the timeline, the deliverables, so on and so forth. So before we get into the webinar for today, I just wanted to give you a brief introduction about who we are and what we do. As I mentioned, my name is Siva Segrin. I operate from the Boston site, which is a global BD center. And XtalPi is an algorithm-driven artificial intelligence-based pharmaceutical technology company. The name stands for Crystal Pharmaceutical Innovation, as the company was founded by three MIT postdocs in 2014 who wrote the crystal structure prediction algorithm. And we have sites in Boston, Beijing, Shenzhen, and in Shanghai. And as I mentioned, we offer both solid state services as well as drug discovery services. And with solid state services, we also offer dry lab and wet lab services, and probably the only, or one of the few CROs, I would say, who has a micro ED instrument in-house. So in case if you have a lot of powder samples and you want to get some crystal structures, we can get it done in 1 or 2 days, or maybe at the max 1 week. And with drug discovery services, we have several AI experts in-house who can help you with the target identification, hit to lead optimization, so on and so forth, with several medchem experts having their input into the workflow, and also synthetic chemistry teams that can not only make the compounds of interest to you, and we can help with accelerating the projects as per the requirements of your budget and timeline. We have lab automation services as well. So if you want to pretty much purchase instruments from us, please reach out to us. We have automation appliances and solutions for both drug discovery, in the sense like for synthetic chemistry, as well as for crystallization purposes. And we also have a XDEL team that is for DNA encoded library. So if you're interested in that, please let me know. I'll be happy to put you in touch with the business development personnel responsible for synthetic chemistry, automation lab, and DEL screening, and XTD, and so on and so forth. So so today's focus is on solid state chemistry and the services we offer in that area. So as I mentioned, with regard to solid form screening and selection, we offer polymorph screening, salt screening, co-crystal screening, amorphous solid dispersion studies, crystallization process development, and scale up from gram to kilogram levels. In the area of computational screening services, we, as you all know, we are an expert in the area of crystal structure prediction, probably the leading vendor in that field. So if you want to completely de-risk selection of a stable solid form in quick time, please reach out to us. And we already walked you through a workflow maybe 6 to 8 weeks ago with a first webinar of this series from Chandler Greenwell on the crystal structure prediction. So if any of you have missed that, please reach out to us. We'll be happy to share the recording of that, and then you can watch it later and get back to us with any questions or comments on that. So today's focus is on the morphology prediction workflow, and we'll walk you through that platform in detail. And let's say if you're an experimentalist or a part of a CRO that you want to accelerate the projects with regard to prioritizing your experiments, then feel free to reach out to us, because we also offer virtual screening of coformers, solvents, and counterions if you're interested in finding a co-crystal, or if you want to understand the propensity of an API to form a solvate, and so on and so forth. So we'd be happy to help you with that in quick time. And those are pretty much a 1 week or max 10 days service lines. And then if you're interested in hiring our FTE-based service models for materials characterization, and then we do offer all the capabilities in-house, as I mentioned before. So feel free to reach out to us, because we offer both fee-for-service as well as FTE-based service models for solid-state chemistry. So let me introduce you to our speaker today. Chandler, as you all know, walked you through our crystal structure prediction platform on Feb 22nd. So he's our in-house expert on computational chemistry, and he did his bachelor's in chemistry and applied mathematics from Weber State University in 2015. He worked as an analytical chemist at Allergan in 2016 and did an internship at NASA Space Mission Analysis Branch in 2018. Chandler received his PhD in computational chemistry from the University of California, Riverside in 2020. His research was focused on crystal structure prediction and electronic structure methods. So obviously he's an expert in that area. So feel free to reach out to him. He lives in Texas, and he loves running, reading, weightlifting, and Legos. And at XtalPi, he's been serving as an application scientist in the Boston BD team, and he acts as an interface between the R&D team and the clients, and is responsible for reviewing reports, handling your concerns about any of the solid state services we offer. And he works on proposals, and he's pretty much a great guy to work with. So definitely feel free to reach out to him if you want to know more about our service lines. So without further ado, let me hand over the screen control to a speaker today. Before I do that, just wanted to alert the audience that if you have any questions during the presentation, please use the questions tab to send in your questions. And it'd be helpful if you could also put in the slide numbers. That would help the speaker to take in more questions during the live Q&A session. And any questions that are not answered during the live session will be answered by the speaker at a later date and will be posted along with the recording of this webinar at a later date. So again, this webinar is recorded, and we'll post the recording and share the link with you at a later date. Okay. So let me pass on the control to Chandler. Over to you, Chandler.
All right, thanks, Shiva. Hopefully you can hear me well and see my screen.
Yes, indeed. Please go ahead.
Okay, excellent. Yeah, so thank you for the introduction, and thank all of you for attending. I'm excited to tell you today about our intelligent cloud-based algorithms for reducing risk in crystallization process development, with an emphasis on morphology prediction. And I'll also talk about a few other topics towards the end, specifically templated nucleation and growth modeling. So the first thing to know is that morphology refers to the external shape of a crystal. And there are a number of properties that are dependent on the crystal morphology, like the bulk density or the dissolution rate, just to name a few. And the crystal morphology has a significant role in chemical and pharmaceutical manufacturing. Specifically, needles, flakes, or platelets can pose development issues because they're difficult to filter, dry, and formulate. Needles and flakes also have poor dissolution behavior relative to lower aspect ratio crystals like prisms. So we definitely prefer prisms, but oftentimes we're stuck with needles or flakes. And these undesired morphologies often add additional costly steps to manufacturing that are used to ensure batch-to-batch consistently. Specifically, techniques like milling or micronization are used to deal with these types of morphologies. But we know that the crystal shape is influenced by many different experimental factors. So you can deal with the crystal morphology either through crystallization itself by tuning experimental variables, or you can use those downstream processes like milling or micronization. There are a number of advantages to trying to improve the morphology through the experimental variables. And I'll just give you an example. On the right here, we have ascorbic acid grown in water, where it forms these square or plate-like crystals, versus ascorbic acid in ethanol, which forms these needle-like crystals. So just by changing the solvent, you can get a much better morphology, preferable morphology, which could help with your entire crystallization process. So obtaining a desired crystal shape and size upstream through experimental design can allow for the optimization of your downstream operations. This can potentially allow for elimination of specific downstream operations like milling and granulation, which can be rather expensive. They can also disrupt things like continuous manufacturing. So our hope is that this computational morphology prediction can be used to help you screen a set of experimental conditions to provide insight to guide your process development. So the first thing I'll show here is our morphology prediction workflow. So the input is a crystal structure that you have, and we'll take the 2D diagram from that crystal structure and we will perform a truncated crystal structure prediction. The purpose of that is to generate crystal structures which we'll use to train a force field. So then we'll take the crystal structure, we'll take the tailor-made force field that we made for this system, and we'll model variables like the solvent, the supersaturation, or even additives, which I'll talk about towards the end. And all of that will be used to make a crystal morphology prediction. And the output is the shape of the crystal under a certain set of experimental conditions. So for those of you who are unfamiliar with morphology modeling, maybe this is the first time you've heard that this is something that can actually be modeled. I'll just give a brief breakdown of the different ways to do this. So the easiest way to do it is what's called the BFDH model. This is a morphology prediction that's based purely on the crystal structure itself. So things like the lattice parameters determine the faces that are morphologically important. We incorporate this into our workflow, but it doesn't take into account any of the experimental variables that you might be interested in. For other more complicated molecules of morphology prediction, they can basically be classified as thermodynamic models or equilibrium models or kinetic models. So there are some software packages that are focused on the mechanistic growth method or these kinetic models. Those are not the models we're using internally. We're focused on these thermodynamic models that we perform with molecular dynamics simulations. Specifically, we use the modified attachment energy model, and we also have an in-house XtalPi method that uses a thermodynamic cycle. And the reason we use those methods is because it allows us to take into account a number of different experimental variables, specifically the solvent mixtures, supersaturation, temperature, multi-component crystals, and also the effect of impurities or additives. And I'll show you throughout the talk how those different variables can come into play with these predictions. The next thing that we use at XtalPi is tailor-making the force field. So at XtalPi, we're very good at molecular dynamics simulations, and we have a lot of experience tailor-making force fields for specific pharmaceutical projects or other chemistry projects. So what I'm giving you here is an example of the tailor-made force field process. So for morphology prediction, in order to describe the energetics of crystal growth, a force field must accurately reproduce interaction energies in the solid phase and also the solution phase. So what we do is we systematically refit force fields to different target properties, and then we perform some benchmark calculations to determine which force field model best describes the system. So in this table here, I've got 4 examples. One is the GAF force field, which is an out-of-the-box force field. It's not specifically parameterized for any of these properties. And the next 3 force fields start from the proprietary XtalPi force field, and then we do some tailored fitting specific for the problem. So for example, force field model 1 was refit to lattice energies and lattice parameters, and also some thermodynamic properties. Force field model 2 was fit to API solvent interactions, and force field model 3 was fit to the solid form properties, the thermodynamic properties, and also the solution interaction energies. And I'll come back to this in a moment with one of the examples. So now I'm going to show you some morphology benchmark studies. So these are some validation studies we performed with this workflow. These are the 6 systems that I'll show examples for. So they range from very classic pharmaceutical test molecules like ibuprofen up to more modern pharmaceutical molecules like palbociclib. So in the previous table, I showed you 4 force fields. 1 was an out-of-the-box force field. 3 were tailor-made force fields incorporating different training parameters. And I'll show you how they perform on a test system of ibuprofen in ethanol. So in the right-hand corner, I have an image here of an ibuprofen crystal that was grown in ethanol. And then this cartoon diagram here, this is the morphology of ibuprofen grown in ethanol based on the measured experimental growth rate. So this is, you can think of this as the true morphology of ibuprofen that we would expect from ethanol based on the experimental growth rates. So in the top left corner, I have the morphology prediction obtained with the GAF force field. So you can see it doesn't match terribly well with the diagram on the right. However, it does have some of the aspects correct in terms of the faces. We see a little bit of improvement when we use force field model 1, which takes into account only the crystal interaction energies and the thermodynamic data. Specifically, we see the 011 face becoming less of the surface area. But then we see further improvement with force field model 2, which only takes into account the solution interaction energies. We start to see thinning of this shape, which is looking more like the plates that are obtained experimentally. But we're still missing the 002 face. It's only with force field model 3 where you're taking into account both the crystal interaction energies and the solution interaction energies, where we get something that's qualitatively very similar to the morphology that's actually obtained. We get this 002 face, and we also get a very thin plate-like structure. So another example using ibuprofen is to show you the effect of supersaturation and how that can be modeled. So the first, the image on the left was obtained in relatively low supersaturation, but when you crystallize ibuprofen with a higher supersaturation, you actually get a change in the morphology. Specifically, you get some elongation about the 002 face. You also see the appearance of this 110 face on the tip of this needle. So we were able to simulate that by increasing the number of API molecules in the solution phase of the simulations. And the combination of a tailor-made force field with molecular dynamics is able to capture that elongation of the 002 face and the appearance of some of those other morphological faces on the tip of this morphology. There are systems that are very sensitive to the supersaturation, like paracetamol. Here I have 3 examples of paracetamol crystals grown in water with a low supersaturation, a medium supersaturation, and a high supersaturation. And we used our in-house model for this, which is an ECM-based method or Einstein crystal-based method. And it's able to capture some of these morphological changes. So specifically, we see a more needle-like shape transforming to a more prismatic shape in the medium supersaturation, and then becoming even more prismatic or almost to the spherical end of things in the high supersaturation. And the method is sensitive enough to capture those types of changes from the modeling. Here we have just a few more select examples that show you how this method works. So we have sal and acetone, and this is just comparing the prediction to the experimental morphology. The NMB and toluene, which always amazes me, right? Because it's kind of a strange morphology that's obtained and predicted quite well by the method. Then we have EPG in chloroform, and also PAL in binary solvent of 4060 butanol and anisole. So this is a needle-like morphology that we were able to capture. So now I've shown some examples where we can model changes in supersaturation and also changes in solvent composition, as you see here for PAL. So now I'll talk about a morphology prediction case study. So this kind of gives you an example of what a morphology prediction project would look like. It's not set in stone. There are a lot of things we can do to tailor the project to a specific problem, but this just gives you an example of the workflow and the deliverables. So in this case, the objective was to predict the morphologies of an API in different solvents. The deliverable was the qualitative shape of the crystal in 8 solvent environments, where moderate supersaturation was simulated in each case. The timeline for these projects is about 4 to 6 weeks, depending on the size of the system and the complexity of the simulations. That's for tailor making the force field, so parameterizing a force field, and also performing the molecular dynamics simulations, plus the data analysis and workup. The workflow for this particular project started with tailor making the force field, which was developed specifically for the target compound using high accuracy quantum mechanical calculations. We identified morphologically important faces for the target compound, and then we used attachment energy and then modified attachment energy calculations with molecular dynamics. And these are the 8 solvent systems that we considered. So this project, and so this is the morphology landscape. This is a concept we developed at XtalPi. This is a way of thinking about all of the ways that a crystal could potentially grow. So all of the morphologies that you could potentially obtain for a crystal. The way we do this is we take the crystal structure and we calculate the morphologically important faces using that BFDH method. And then we use some descriptors, specifically the shape factor and the anisotropy, which are essentially 2 different ways of measuring the deviation from a sphere. So you go from very spherical morphologies in this bottom left corner to needle-like and plate-like morphologies as you go up and across, respectively. And the way we obtain this is we take those morphologically important faces and we vary the surface areas that you could potentially obtain. That allows you to basically explore the landscape of the possible morphologies by sampling different surface areas for those morphologically important faces. And the 2 descriptors allow us to calculate them. For each morphology, we can calculate those descriptors, plot it, and then we can calculate the kernel density estimator based on the types of morphologies for that system. So a denser area of this plot means that there are more morphologies that are potentially available within that region. So in this case, we see that there is the potential for lots of prisms or plate-like structures based or suggested by this morphology landscape. However, the experimental results obtained up to this point had yielded needle morphologies. So there was this flat needle obtained in a mixture of MEK and water, and also this needle obtained in ethanol. So the first thing to do was to verify whether or not the simulations could predict these results. So in pure MEK, we get something that's very similar to what was obtained in MEK and water. And we could do a binary solvent system. That just wasn't what was asked at the time. And in pure ethanol, we obtained something very needle-like and very similar to what's obtained experimentally. So then the next step was to go into solvent systems that hadn't been explored experimentally. So here we have ACN and THF, in both of which we predicted needle-like morphologies. In ACN, we predicted very extreme high aspect ratio needles. However, we predicted different morphologies in some other solvent systems. So we see some plate-like morphologies that are predicted, and even some thicker plate-like morphologies predicted in toluene. So moving into an area of more desirable morphologies, at least the simulations suggest that that should be possible. And you can put this all together by taking the morphology landscape for this particular molecule, or crystal structure, I should say, and then plotting the predicted morphologies on that morphology landscape. And then we can indicate the solvent system or experimental conditions that yielded that particular morphology. So you can see we have more needle-like predictions in some solvents and more plate-like or even thick plate-like structures in other regions. So this data can all be taken and used to design more experiments. So now you can imagine using some solvent combinations or even exploring some solvent systems with different properties in order to try and push the morphology into even more desirable areas of the morphology landscape. So that's an example of a case study. And now I want to show you a recent R&D project that we did in collaboration with the Merck Group in Germany, where we modeled the effect of polymer additives on crystal growth of metformin HCl. So metformin HCl is a drug used for the treatment of diabetes. And it has some interesting properties in terms of the effect of additives on its morphology. So in pure solvents, metformin HCl yields needle-like crystals, but it's been observed that polymer additives and some other additives can yield much more desirable morphologies. So when we were discussing a potential morphology project, this particular system came up, and the challenge posed to us was basically, are the simulations able to capture this effect that the additives have on metformin HCl? So we took up the challenge, and the result is this recently published article, The Effect of Polymer Additives on the Crystal Habit of Metformin HCl. This was published in the Small Methods Journal. So if you're interested, please take a look at this, and I hope you enjoyed that. And now I'll go through some of the details of the study. So in terms of the scope of work, this again started with the tailor-made force fields that were developed not only for the API molecule of interest, but we were also able to customize some force fields for the polymer additives using quantum mechanical calculations. We used the modified attachment energy method with molecular dynamics. That was the workhorse of this study. We developed many different force fields to compare how they performed on the system. So we've developed a way to not only parameterize those, but also evaluate their performance. We also looked at the effect of polymer chain lengths and also the effect of varying substituents for the case of HPMC. And we performed morphology predictions under the following experimental conditions. So we looked at five simulations performed in MEOH and 2 performed in an IPA water mixture. 2 of the simulations did not incorporate additives, and the rest of them had different additives in them. And we used a supersaturation of 1.65 for all of these simulations. We calculated the morphology landscape for metformin HCl, and this is what it looks like. So we see that there are possibilities for prisms, needles, and plates. And then I've put the percentage breakdown. You'll notice some numbers next to some of these morphologies. That gives you an idea of the most probable morphologies based on this morphology landscape. So we see that prism habits are very probable based on their probability density, and then they go down from there. So like this would be the 10th most probable shape that we see up here, or 12th most probable, or 3rd most probable here. And then we took similar morphologies and we grouped them together to give you an idea of the distribution. So Based on the morphology landscape, 43% of the predicted morphologies are prisms, 22% are plates, and 35% are needles. So there is a high chance of obtaining prisms for metformin HCl, but there's also a significant risk posed by needle morphologies. The next thing I want to explain is the force field fitting. So the first thing to do was to tailor make a force field for the crystal itself. So we looked at, and there was an additional challenge that metformin HCl is a salt. So we had to consider that as well during the force field parameterization. So in doing that, we looked at the API and chloride interactions. We also looked at the salt and ethanol interactions and salt and water interactions. And taking all this into consideration, we trained 5 different force fields, and those were refit with various interactions that we obtained up here. So like, for example, force field 2 was refit to crystal structure prediction of metformin HCl. Force field 3 was refit, took the CSP force field and was refit to API chloride dimers, and they get more complex from there. And then we were able to verify the force field performance. So we took the force fields that we parameterized and we optimized metformin HCl crystal structures, and then we compared those structures to the experimental structure. So you can see the out-of-the-box force field is not even able to reproduce the crystal structure, versus the tailor-made force fields, which are all able to reproduce it, except for force field 5, interestingly enough, suggesting it might be overfit. But force fields 1 through 4 all reproduce the structures. So then we made our selection based on the RMSD 15. We selected force field model 3 because it has good performance and also takes into account not only the CSP refitting, but also the API or the salt interactions. We also were able to make tailor-made force fields for some of the polymers. So this is an example of that work. We came up with a parameterization procedure for that. So in that case, we looked at salt and PEG interactions, and also the interaction with the polymer with the solvent system. So to do this, we made truncated versions of the polymer. So example, PEG former means that there were 4 repeating units of PEG. That was deemed to be large enough that we could get some of the effects of the molecule, but small enough that we could perform the quantum mechanical calculations on it. And then we trained a number of force fields based on those interaction energies, and we ended up going with force field model 4 in this case, which takes into account the interaction between the salt and the polymers, and also trimers of the polymer units and the solvents. So now that I've given you basically all the work that was done for parameterization of the force field and the morphology landscape for metformin HCl, now we can look at a comparison of the predictions that were calculated compared to the experimental results that were obtained by Merck Group. So the first is if we look at metformin HCl grown in a solution of MEOH. This is a PLM image below that was obtained from the crystallization experiments. And we see that these are very needle-like crystals, and the calculations are able to reproduce that qualitatively very well. Then we look at experiments that incorporate PEG or tween, and we see a dramatic change from the experimental results. We go from these extreme needles to much more block-like morphologies, and we're able to capture that qualitatively very well with the predictions. Something else I want to call your attention to that I'll talk about more towards the end of my talk. You'll notice here that you can see the crystal faces that dominate or make up the morphology. So in pure MEOH, we see that the 100 face is by far the dominant face of the morphology, and we see a small percentage of the surface area taken up by the 110 face. But when we add PEG or tween, we see that the 110 face disappears from the morphology and it's replaced with the 020 face. So we'll talk a little bit about how that happens later on and what the simulations can tell us about that specific change. Here we have a few more examples from MEOH. So specifically, this experiment was MEOH with PVP. So interestingly, PVP does seem to change the morphology from pure MEOH, right, where we get extreme needles, but we don't see the same type of change that we see with some of the other polymers. We still get a fairly needle-like crystal, and the simulations are able to capture that, right? So what we're seeing is that 110 face doesn't disappear when the PVP is added. Therefore, you don't shift away completely from a needle-like morphology. Here we have an examples of HPMC with two different repeating units. So both of them give us something very different from a needle. They give us these very box-like morphologies, and those seem to be qualitatively very similar to what was obtained from the experiment. So we see a very large change in morphology when HPMC is added. Next, we have the IPA water. So this is a binary solvent prediction. Experimentally, we see we get these needle-like morphologies, and they even tend to agglomerate. But the morphology prediction calculation is able to predict those needle-like polymers, or morphologies. And then we have a simulation that takes into account HPMC. And when experimentally, when you do that, you deviate away from the needles, you get something very block-like or very prismatic, and we're able to reproduce that with the calculations. So overall, the calculations seem to be very successful at reproducing qualitatively the changes that we see in the morphology of metformin HCl when these polymers are added. We see the effects seem to be distinguishable based on which polymer is simulated. So that's very exciting. The next thing we want to do is explain from a molecular level why we see those changes in morphology. But first, we'll just visualize the effect that the additives have on the morphology landscape. So this again is the morphology landscape for metformin HCl, and we can plot the morphologies that we calculated under the different experimental conditions. So the most needle-like morphologies are for the pure solvents. So we have IPA water over here, and then we have MEOH here. The next is PVP, where we saw that we obtained some fatter needle-like structures, but we didn't deviate away from needles altogether. Those are here clustered together. And then we see down in this other region of the morphology landscape, the simulations that yielded much more prismatic or box-like structures. So remember, the morphology landscape suggested that prisms were a likely morphology for metformin HCl. And by using polymers, you're able to access that region of the morphology landscape. So by tweaking the experimental variables, you're able to significantly modify the morphology and obtain something that's much more desirable from a process standpoint. Next, I want to talk about the molecular level insight that we can obtain uniquely from these calculations. So this is something that would be very hard to get from experiment. And we found from our calculations that there were essentially two mechanisms by which the morphology of metformin HCl can be changed by these polymers. This one, the additive binding to the surface, I think if you were to make a hypothesis about how polymers can change morphology, I think this would be probably the instinctual explanation, right? That if you put the polymers in the crystallization batch, they bind to certain surfaces selectively and basically block API molecules from growing on that surface, right? I think that's intuitive. And we did see a lot of that based on the yellow, orange, and red blocks in this matrix here. But we also found that there's another mechanism whereby the polymer disrupts API solvent interactions. So in this case, solvent molecules actually bind to the surface and block the API from growing on that surface. So you can imagine how that can slow down the growth rate, therefore making that face more morphologically important. But the polymer can disrupt those interactions and allow the API to start to grow on that surface. And we saw both mechanisms. Specifically for the 020 face, we saw the latter mechanism where the polymer disrupts the API solvent interactions. And then for many of the faces, we saw that it was the effect of the additive binding to the surface. Now, we did notice that the polymers do modulate the growth rate of all the surfaces, but what we found is that for the fastest growing faces, slowing down the growth rate a little bit didn't have a profound effect on the morphology, because even though you've slowed the growth rate a little bit, proportionately, you didn't slow it down enough to make that face morphologically important. Rather, we saw that the polymers have the greatest effect on the faces that are already growing slowly, specifically the 100 face, the 020 face, and the 110 face. And we saw something interesting here. So if I go back to the first example I gave of MEOH, remember that we have this 110 face, and that disappears once we add the polymer. So what we realized is that changing the growth rate slightly has a profound effect on certain faces. So for example, when you add the polymer, you essentially turn off the 110 face. So you have a real face that you're turning off. So now that's a virtual phase, or what we would call a real to virtual transition. We have the opposite effect for the 0 to 0 phase. So it's not seen in the pure solvent. So it's a virtual phase, right? It could exist, but it's not accessed in that solvent system. But when you add the polymers, they change the growth rates enough for this phase that you see that 0 to 0 phase appear in the morphology. So you have a virtual to real transition. So it was those real to virtual and virtual to real morphological phase transitions that allow us to change the morphology of metformin HCl so profoundly. And that's because the polymers, the effect that the polymers have on the growth rate of those specific faces is profound enough that it can essentially switch those faces on and off, and the result is a totally different morphology. Whereas for the fast-growing faces, small changes in the growth rate or in the binding energy aren't enough to significantly change them morphologically. So what this tells us is that systems that might benefit from this type of additives, including additives, are ones where there are faces that small changes in the growth rate can have a profound effect on the morphology. And the modeling that we've performed here can give you that type of insight. So I'm going to conclude the discussion of morphology prediction with this, with some of the project parameters or the project requirements. So the input for this type of model, the thing you absolutely have to have is a crystal structure file. So that can be a CIF file of the API. That can either be obtained through experiments like an STXRD or microAD experiment, or that can even be a CSP predicted structure. Then you need some experimental conditions to simulate. So here I've listed 15 solvent systems, but we could vary that, right? We could look at different supersaturations. These are MD simulations, so you could potentially look at different temperatures, and you can definitely incorporate additives and polymers, as I showed with the last example. So that's definitely an exciting option for this type of project. The output is the qualitative morphology prediction in each solvent, or more specifically, each experimental condition that we simulate, and also the morphology landscape. The timeline, again, is 4 to 6 weeks. And some limitations, so this is a thermodynamic model, right, that I've shown here. There's no kinetics involved, so we can't simulate the effect that seeds might have on crystallization. And in terms of impurities, we've never done a project with impurities on the crystal faces. You can imagine that maybe the MD simulations would be sensitive to that. It's something we could potentially explore. We just have no data for that at this time. This stipulation, we've never encountered this, but if you have a crystal structure with a really high aspect ratio of one of the crystal lattices, potentially the simulation size would be too large. Again, we've seen some rather large aspect ratios, and we've never encountered that, but it's just a potential limitation. The method, again, is molecular dynamics with a tailor-made force field, and we'll use most likely the modified attachment energy model. But if you have some data that suggests that maybe the system is highly sensitive to a variable like temperature or supersaturation, we could explore using the Einstein crystal method for that type of project. And then some other requirements that are good to have but not necessary for the project, things like solubility data. That way we can set up the predictions under the experimental conditions. If not, we can just use a moderate supersaturation for the calculations. Also, thermodynamic data like heat of fusion, that can benefit the force field fitting procedure, but it's not necessary to get good results. For example, for the metformin project, we didn't use any thermodynamic data in the fitting. So that concludes the discussion of morphology prediction. I just want to show a couple more slides about modeling templated nucleation and growth. So this is I would say some of the protocols for this model are very similar to morphology prediction, although the outcomes are quite a bit different. So what would be the motivation for modeling templated nucleation and growth? Well, first of all, crystallization can be slow, but templates can enhance the nucleation kinetics. So templates can be used to grow crystals faster, right? Which could be a benefit for process. Also, templates can be used to obtain desired polymorphs selectively. So if you have competition during crystallization or a particular form you want to target, you could potentially use templates to try and target crystallization of a select form. In both cases, modeling can be used to screen different templates and explain at the molecular level why the template works. So the workflow for this type of project, it starts with the inputs, which are the API, the solvent, and also a polymer library, but this could also be a crystal template library too, depending on what kind of templates you're interested in modeling. We'll then do some fragment-based DFT calculations for force field fitting, and we'll determine the API and polymer or API and crystal interactions. Then we'll identify the relevant faces using the attachment energy and BFDH. And then we'll characterize the polymer or crystal surface, and we'll set up a simulation that looks something like this, where you have the template being much larger than the crystal slab, and we're going to identify and model how the crystal moves over that template. From those MD simulations, we'll get the energies of interaction and some other useful descriptors, and we'll use those to rank order the polymer or the crystal templates by their ability to induce nucleation. So that would be the ultimate output, is the templates that we think interact best with the crystal and give you the best chance of nucleating that particular crystal. I don't have any specific project examples for this, but I'll just mention some projects that motivated this type of work. For example, this project, which looked at the nucleation of paracetamol in acetonitrile on these biopolymers. So this is an interesting paper if you're curious how that worked. And another use case also performed on paracetamol where in ethanol, where hydroxyl-rich crystalline substrates were used for template nucleation and growth, and MD was able to model that as well. So on that note, I'd like to thank you for your attention, and I'm happy to take any questions you have about morphology prediction or maybe even templated nucleation and growth.
Thank you, Chandler. It was a fantastic presentation on morphology prediction, and I'm sure the audience out there would understand the value of getting insights into the effect of solvents, polymers, and additives. If you're working in downstream milling process, then this morphology landscape takes this to a whole new level, I guess. So the session is now open for question and answers. So let's see. The first question is from a former speaker, Eric Tybeck. So question is, can you describe how the ECM is used to predict morphology, and is the same ECM thermodynamic cycle that you use for finite temperature corrections to the CSP?
Yeah, so Eric, we can definitely discuss this offline, or we could have a pretty in-depth conversation about this. But yeah, it's based on the same thermodynamic cycle, but the outcome is to get the morphology prediction rather than the Gibbs free energy of different crystal structures.
Okay. The next question is from Veeraswamy Rama, and the question is, can we predict polymorph by checking morphology?
Can we predict polymorph by checking morphology? So the MD simulations that we use for the morphology prediction, they by design will not show us a polymorph transition. But what we could do, since the input for morphology prediction, here, let me go to the workflow slide. Yeah, so since the input is the crystal structure, right, what we could potentially do is do predictions on two different polymorphs, right? And then we could look at the interactions between the solvents and those particular polymorphs and the morphologies that were predicted. What we could also do is potentially a templated nucleation and growth project there, right, where we could look at how different templates interact with those polymorphs. But by design, these simulations shouldn't show us a polymorph transition. That shouldn't happen. They're not designed for that.
Okay, great. The next question is from Satish Ayam Perumal. So the question is, can you describe how you're calculating the contours in the landscape? Do you have a sense of errors on the numerical value of predicted stability? I think he's referring to slide number 22.
Let me go to slide 22. So this is slide 22. This is, are you sure we're not talking about the morphology landscape? Oh, here we go, slide 23. Yeah, so the contours on the landscape are calculated with a kernel density estimator, and that's based off the two descriptors that we use, the anisotropy and the shape factor. In terms of error, I don't know that there are any error bars specifically associated with those. So the way we do this, right, is we take the crystal structure that we're interested in, and we determine the morphologically important faces with the BFDH model. So that tells you in this case, right, so we can see that the BFDH gives us 1, 2, 3, 4, 5, 6 morphologically important faces. And then we can vary the surface area of all those faces manually. So by varying the surface area, you're effectively, if you increase the surface area, you're essentially saying, what if that face grew more slowly? And we do that for all of the faces, and that's how we get all these different shapes. And then we calculate the variables, the shape factor and the anisotropy. So since we're manually changing those and calculating these descriptors, I don't know if that there's an error bar associated with that. But then the contours themselves come from a kernel density estimator based on these two descriptors. So I hope that answers your question. Maybe I can discuss with the team and get back to you if there's what we think any particular errors would be for this. But I think because it's manual, that there wouldn't be any specific errors there.
Okay, great. The next question is, for handling polymers, did you see a local minima? Let's say the polymer coiling up throughout the simulation, or did the MD length scale capture both coiling and recoiling?
So obviously the polymers could be very, very long, right? So we did have to make some assumptions about the polymer chain length. So we made them small enough, but you see a lot of dynamic behavior of the polymers in there, especially as they're kind of wiggling through the solvent layer and in the way that they attach to the surface. So in terms of coiling and uncoiling, I don't know that we examined that specifically, but they did move very dynamically throughout the simulations based on the polymer chain length that we used. But we did use fairly short polymer chain lengths in order to make the calculations tractable.
Mm-hmm. Okay. Next question is, you mentioned crystal structure prediction as a part of the morphology prediction workflow. Can you elaborate on that? Is it necessary to do morphology prediction along with crystal structure prediction?
Yeah, let me go back to the workflow slide and I can comment on that. Yeah, so as mentioned, the input for morphology prediction is the CIF file. Where the crystal structure prediction plays into account, that's for the tailor making of the force field. So I think hopefully I've impressed the point that the ability to tailor the force field for these simulations is part of what gives them predictive accuracy. If you just use an out-of-the-box force field, you're going to get much less qualitatively correct structures. So our crystal structure prediction algorithm involves a step for tailor making the force field, because you get these crystal structures and you get different crystal structures specifically, and you can pull out dimers and monomers from those structures and use those quantum mechanical energies to tailor make a force field. So what the crystal structure, the truncated crystal structure prediction does is it gives us a data set of crystal structures from which we can draw the dimer and monomer interactions and then tailor make the force field. So let me go, yeah, so right here, right. Let me find the slide just to give the example. Here we go. All right, so in this slide, I'm showing the force field parameterization procedure. So you'll notice FF1, this is just our in-house, this is one of our in-house force fields, right, without any tailor making. And then we refit that force field to the CSP structures, and then you can go further and do further tailoring. So the bare minimum tailor-made force field we want to use is based off those CSP interaction energies.
Okay. The next question is, can you do morphology prediction on a multi-component crystal?
Yeah, we can. Let me go to the table. Yeah, so here where we're looking at what the different models can handle, the modified attachment energy checks all those boxes, including the multi-component crystal, and even the BFDH, because it's just based purely on the lattice parameters. It can tell us the morphologically important faces for multi-component crystal, and then we can do the MD simulations on those particular faces.
Okay. The next question is from Shenglin Zhu. The question is, in morphology prediction, how the mass transportation is considered in the model when the kinetics of different phases may be limited by this transportation?
That's a good question. So again, this is the thermodynamic model, not a kinetic model. So we're not really taking any kinetics at all into account, right? This is an equilibrium model where we're basically getting the growth rate by determining the equilibrium between the surface and the API molecules in the solvent. I'm wondering if, based on the trajectories of the simulation, if we could give any sort of insight into that. I think we'll have to get back to you on that question after thinking about it carefully.
Okay, that sounds good. The next question is, what if the morphology calculations end up predicting only needle habits?
Yeah. So that's possible, right? Let me go to a morphology landscape. Okay. So for every system that we've studied, the morphology landscape is unique, but it does usually encompass some combination of prisms, plates, and needles. So I guess the question here would be, what if we did 15 simulations and all of those simulations predicted needle-like structures? That would be, I guess, a little bit unfortunate because it would suggest that the experimental variables like solvent or supersaturation are not enough to change the morphology. Maybe you would see that with a very high aspect ratio crystal. It's just, based on the lattice, it might be predetermined to form needles. That would be unfortunate if we found that if we simulated that the experimental variables can't change the morphology, but that in and of itself would be a useful result, right? Because it would basically tell you, presumably you would have performed some experiments too, where you were only obtaining needles, and then you would have this modeling data that would suggest that only needles were possible. And that would basically tell you that you're stuck with needles, and you can move on to trying to mitigate the morphology or planning ahead for your process that you're going to have to do some sort of downstream processing, right? And you would have both the experimental and the modeling data to back up that decision. And so hopefully it would allow you to plan accordingly. So I think that even though it's not necessarily the result you would want, I think it would be important for guiding your decision making nonetheless.
Okay. The next question is, in addition to additives, can you also simulate surfactants?
Yeah, definitely. In fact, they're really similar. So some of the same protocols we used, and I believe tween is kind of somewhere in between. Let me see here. We looked at, just go to the metformin study. Yeah, so we looked at tween, which I believe is somewhere between a polymer or a surfactant. So we can definitely do surfactants, and we would adopt our methods, similar procedures to what we used for the polymers, but we could adapt those for surfactants. So yeah, we would definitely take that project on, and I think we'd be quite successful.
Okay, time for two more questions. So the next question is related to slide number 35. Is the input for templated nucleation and growth model the 2D diagram of the API or the crystal structure of the API?
Yeah, so so I've got API here, but yeah, this would be the crystal structure of the API, right? So if you look down in this picture here, what we're modeling is, you've got a template that could be a polymer template or a crystal template or some other template that you're interested in, and then the crystal structure as well. And you're basically modeling the interactions between that crystal and the templated layer. So the input would be the crystal structure.
Okay. The next question is, what's next for the morphology team? Is this approach also transferable to clients in the other industries like batteries or nutraceuticals and so on? Like, what's the next challenge?
Yeah, so I think all the examples I gave in this talk were pharmaceutical molecules, right? That's because it's very well documented, the challenges that morphology has for the pharmaceutical industry, like specifically for processing. Hopefully that was apparent from my motivation slide. but these workflows apply equally well to other small organic molecules, right? So if it was an agrochemical or a nutraceutical compound, there's no reason why we couldn't use these workflows for that. Maybe even an organic semiconductor could be an interesting project. Those are small organic molecules. We've done some projects, crystal structure prediction projects on those types of molecules to some success. And I know in organic semiconductors, sometimes you have thin films or other properties that are very dependent on the crystallization. So that would be a super interesting project, and I think would be really successful. In terms of other materials, like batteries, those involve inorganic molecules. There's lots of modeling tools out there for inorganic systems, and in some ways, if you can model crystal structures or organic molecules, there's a lot of simplifications you can make for inorganic systems. So I think potentially some of these workflows could be adapted to look at inorganic systems. So it would probably fall in the realm of an R&D project, but I think we'd be interested to try that out. We certainly have the talent to do a project like that at XtalPi. We have a very big modeling team.
Great. Okay, the last question for the session, and it's from my end. Since a lot of grad students are also attending these webinar series pretty regularly, what would be your career advice to grad students who are currently working as a computational chemist? What kind of skill sets should they pick up going from academia to the industry, especially to work in a pharmaceutical industry and study morphologies or crystal structures, and so on and so forth?
Yeah, that's a good question. Okay, so yeah, if your goal is to get into industry, then I definitely would have a talk with your advisor and try to angle some of your projects to an industrially relevant project, right? Something that people are working on. If you want to go into industry from academia, internships are really important. Some majors emphasize this more than others. Like, for example, all my friends that did engineering, you basically have to do internships throughout your engineering degree. I would love to see chemistry and related fields put more emphasis on internships, even in your PhD. So I did an internship when I was working on my PhD, and it was immensely beneficial. And my advisor let me do that internship, right? He could have said no, he didn't say no, he said yes. And yeah, that can be beneficial for several ways, right? It gives you the experience and the connections, because connections are important, which leads into my final bit of advice, that the soft skills are really important too, right? I think if you're doing a PhD in material science, then your technical skills are probably pretty good and getting better every day that you're working on a project, but the soft skills are really important too. So you definitely, it helps to know the right people, and it definitely knows how to, helps to know how to sell yourself and your skill set. So internships, soft skills, and choose your projects and advisor carefully, right? Make sure that whoever you're doing your PhD with, it's a long time. So make sure they're aligned with your career goals.
Very good. So, I mean, before I end, I think there's another question that just came in at the nick of time. So the question is, if only needles are possible from the modeling and experiment, is it possible to predict a suitable additive to modify the needle into a different morphology? And this question is from Joanna Biss.
Yeah, so let's take a high aspect ratio crystal, for example. Let's imagine that one of the unit cell parameters is just really long compared to the other two. The way that the unit cell is for that crystal is you'd be almost predisposed to needles. So it's very unlikely that just changing the temperature or the solvent composition is going to have a profound enough effect on the growth rate that it would change that molecule from something other than a needle. And that's really where polymers or additives might come into play, right? That would essentially be, if you're determined to change the morphology from the crystallization, I think polymer additives or surfactant additives would be your best chance. But there would be no guarantee, right? We saw, let me go back just a slide or two. We saw that the modeling can tell you, we saw that the polymers change the growth rate of all the faces of metformin HCl, right? But for fast growing faces, it just doesn't change it enough that it can stop those faces from essentially growing their way out of the crystal. It's the slow growing faces that are changed the most by small changes to the interaction between by those small interactions. So if that was the specific goal, we would want to do a few simulations with some polymers of interest. We would do maybe 5 to 7 calculations, and then we would do, based on those results, and specifically a map like this that would tell us about the interactions, we could maybe pick another set of 7 to 8 polymers or surfactants to try and exploit certain interactions. So the short answer is yes, we could simulate that with that goal in mind. There would be no guarantee of finding a polymer that could have that effect on your pharmaceutical, but I think it would give us the best chance of designing, of one, finding if we could change those properties, and two, which polymers or surfactants would lead to that desired change.
And will the model tell me what specific additive would have best changes in the modification, or?
Yeah, it should tell us that exactly,
Okay.
right? It should tell us, one, through the predictions themselves, right? So we can see, like, just this example here, going from pure IPA water to adding HPMC, right? We see there's a profound effect, but also this type of analysis here tells you why it has that effect, right? And specifically what faces are most effective. And that's on a polymer basis, right? So for each face, we looked at the interactions with each polymer, so that this type of analysis should tell us exactly why the polymer is having the effect that it's having, and then we can, pick other polymers with similar properties, right? If we want to try to explore that property in depth.
Great. Thank you, Chandler. With that, we have come to the end of this webinar today. Okay, that was a fantastic presentation. I really appreciate you taking the time to walk us through the morphology prediction workflow. I'm sure the audience would have got a lot out of this presentation today. And if you have more questions or comments, please reach out to me. My name is Siva Kumar Segran. I'm the Senior Director of Business Development at XtalPi, in charge of solid state services. So feel free to reach out to us with any questions or comments or any topics that's of interest to you that we could cover in the next webinar. As I mentioned before, we offer solid state services, drug discovery services, synthetic chemistry services, and lab automation appliances and solutions. We have several BD representatives who are in charge of each of these service areas. So please reach out to us if you have any questions, and I'll be happy to put you in touch with the correct BD person that can help you with and walk you through the whole process. So thank you everyone again for taking the time to attend this webinar on morphology prediction. And we look forward to meeting you again in another interesting webinar pretty soon in the next few weeks. I'll keep you posted on that. And in the meantime, definitely reach out to us with any questions and comments. Thank you and take care. Goodbye.